Welcome. Let me say something about soft barycentric refinement. Again, the definition has adapted a little bit in such a way that the manifolds with boundary are preserved. So that was not the case before. For this pair of simplices, this would just go down to a one-dimensional simplex, and afterwards to a zero-dimensional simplex, it would disappear. But if we take the definition, adapt the definition, and also include the facets of the boundary, include them in the new vertices, then we get a much nicer version of barycentric refinement. And what happens is that the barycentric refinement of the boundary of a manifold with boundary is just the usual barycentric refinement. So there is a kind of in the interior it's more soft, right? Here when we would take barycentric refinement here, the vertex degrees would double each time in the interior, but in this case it just stays 6 and stays flat. It is a nice version. But on the boundary, what happens on the boundary? In the boundary we still double. On the boundary it's the usual barycentric refinement. And that's especially from dimension 3, if you take three-dimensional complexes, this is nice because we have less simplices and still nice three-dimensional spaces. Now, I'm interested in the spectra, what happens in the limit when you do that refinement again and again and again, what happens in the limit. And similarly then in the barycentric refinement, there is also universality in the soft barycentric refinement. The reason being is that the simplices, just the maximal simplices, the number of maximal simplices explodes exponentially, and the boundary simplices of dimension 1 less grow less fast, slower, also exponentially but slower. And what we have seen already, I talked about this in dimension 2, what happens is we can, via Fourier transform, we can really get the spectrum of the hexagonal lattice. It's in the limit we get the hexagonal lattice, and in this case we can actually compute in principle we can compute the Fourier transform, and then we have a a absolutely continuous measure. In the one-dimensional case it's also absolutely continuous. This is the arcsine distribution, but in dimension 1 less. Now, over the break, I was looking at the spectra in dimension 3. So we take a three-dimensional complex and we refine it and we look at the spectrum. And it looks as if this spectrum, maybe I show a picture, it looks as if this spectrum is very much related with the spectrum of the barycentric refinement in dimension 2, dimension 1 less. So this suggests, because it's true in dimension 2 and in dimension 3 there's strong evidence. I also made experiments with dimension 4. Of course it's getting harder and harder to make experiments, you can do less iterations, but it looks as if the gap structure of this Cantor type measure, universal measure, is that they are related. Maybe related in such a way that they are mutually absolutely continuous with respect to each other if you allow deformations. So it's not that it's just absolutely continuous, but after a deformation becomes absolutely continuous. And also this is an equivalence relation between measures, which for example would imply that the spectral type is the same just for the barycentric refinement and the soft barycentric refinement for one dimension larger. So this is what I wanted to tell today.